I don't know.
Start. Go.
We should start?
Yeah.
Can we close the door? Thank you. Okay. Hello. My name is Rasul Tutunov, and first of all, I want to thank all of you who came today on my talk. Today, we're going to present the first distributed Newton method for large-scale global consensus problem. This is a joint work with Haitham Bouamar from Princeton University and with Alijat Babai from University of Pennsylvania. Well, yes. So let me start with some brief motivation and problem definition. Machine learning nowadays is being used everywhere. You can find applications in marketing, in finance, in robotics, in network analysis, and so on. But when the data grows large, the standard centralized solutions for machine learning problems become inapplicable. Therefore, the goal is to handle big data problems with the distributed solvers, which distribute this data across the multiple processors. And we will look the solution in a distributed way that only allow the local communication between these processors. Let me give the simple example for the linear regression problem. In the linear regression problem, you're given the data set that consists of input-output pair. Each input point xi is a vector in d-dimensional space. Output variable yi is just a scalar. Assume we're given m these data points, m these pairs, and our goal is to find a function which is parameterized by some unknown vector theta, such that this function actually describes the dependency between input and output variables. The standard way to solve such kind of problem is called the square method, and it's presented on this slide. It's nothing but the minimization of the summation of these two terms. The first term here, it's called data feed term, and actually it reflects the dependency between input and output pair. And the second term is called regularizer, and it's usually been introduced either to avoid the overfitting of the model. In this case, we use L2 norm. And in the case where the feature space is very highly dimensional, and we want to sparsify the features, so we want to find the most relevant one, we can use L1 norm as our regularizer. As you can see, when m here grows large, this problem is difficult to handle in the centralized way. So therefore, let us assume that we can actually distribute these m input data points across, let's say, n nodes that are combined in some graph topology, in such a way that each j node will get exactly mj data points from the data set. Then this objective function can be written in this way, in the following way, where we have these local data feed terms plus regularizer. And because we want to find the solution such that for all these nodes, this theta vector will be the same, we have to impose the global consensus constraint, which represented as this constraint. Theta 1 is equal to theta 2 is equal to theta n. Looking at this problem, we actually can define it in a more generic way that we will refer as a global consensus problem. So the goal is to find the minimum of the summation of the local objective functions, fj. It depends on the unknown parameter theta j, such that the global consensus requirement must be satisfied. Because our goal is to find the solution in the distributed fashion, we need to rewrite that problem in the equivalent form that will allow us to use the implicit decentralized structure of the problem. In order to do that, firstly, we introduce new variables, vector y1 to yp. Essentially, these vectors, they collect all the components of the unknown vector for the original problem. So y1 will collect all the first components of the vector, theta 1, theta n, y2 all the second, and so on. And also, we need to rewrite the global consensus constraint in an equivalent form by this linear system. Here we introduce new block diagonal metrics that we will call M, and on each diagonal we have a Laplacian graph as the element. So it's very easy to see that these two problems are equivalent, because if the graph is connected, we know that the only vector which corresponds to the zero eigenvalue is the vector of ones. Therefore, if that constraint is satisfied, it means that all first components of vector theta's are the same, all the second, and so on. So it's really two equivalent problems. Looking at that problem and fetching the goal to solve it in the decentralized way, we recognize three possible techniques that can be used. The first one is a well-known gradient descent, distributed gradient descent. Although it's successful, it suffers from the very slow convergence rate, which is characterized by law O1 divided by root square of t, where t is the iteration count. The second is distributed ADMM, alternating direction method of multipliers. Although it improves the convergence rate to 1 over t value, it suffers from the low precision when it comes to the consensus error. It took many iterations for the ADMM, distributed ADMM, to converge to the solution that actually has really close theta vectors for each node. And the third approach is the second order method. And the first such method was proposed by Ryan, and it's called Newton network. In that algorithm, they try to approximate Newton direction by considering the truncated sum of the Taylor expansion of the Hessian inverse of the primal problem. They proved that the convergence rate is linear as an ADMM, but in our experiments we noticed that for the very highly dimensional problems, it fails to outperform ADMM, so ADMM performs better. So consequently, we can ask a question: can we find the distributed second order method that, first of all, can approximate the Newton direction step with any arbitrary precision in the distributed way? Second, can outperform all the existed methods, both in the convergence rate and in the precision value of the output solution? And third, that will exhibit superlinear convergence rate in the neighborhood of the optimal solution. And today in our talk, we actually we will see that we designed the method that satisfies that requirements. Before to jump to the technicalities of the approach, let me briefly mention the important and crucial properties of the dual function of the problem that we will consider. So, as I said, we go for the standard primal dual approach. For the primal problem here, we define the corresponding dual, by introducing the new dual variable lambda, which is np-dimensional vector. And this vector consists of p n-dimensional vectors, lambda 1, lambda n. Intuitively, for each node I, each node I will store the ith component of each of these vectors. Therefore, we can actually write the dual problem in the following way. And the first observation that we can make that this dual function can be fully distributed, in the sense like in order to compute each ith value of that function, the only information that node needs, either it's stored in that node, or it can be received by that node by just sending and accepting messages from the immediate neighbors. As we said, that there are two very important properties of the dual function that will be exploited in order to get our method. And these properties are presented on this slide. First of all, we proved that the Hessian of the dual problem has that form, where M is that block diagonal matrix that we introduce in our constraint. And the gradient has this form. And the second property is that the Hessian of the dual problem actually is ellipsis continuous with respect to the norm defined by this block diagonal matrix M. And the parameter B depends on the topology of the network that we consider. We're going to exploit these two properties in order to get the distributed Newton method that can approximate the Newton direction with any arbitrary precision. So let us start with the standard Newton type iteration scheme for the dual problem. So essentially, the dual variable at k plus 1 iteration is equal to the dual variable at k iteration plus step size multiplied on the approximate Newton direction. The challenge, however, is to get the Newton direction in a decentralized way with any arbitrary precision. Recall that the exact Newton direction can be found by a solution of this system of linear equations, where hk is the Hessian and jk is the gradient. Using the first property that we mentioned above, we know that this system can be written in that way. And crucially, we can now observe that in order to solve that system, we actually need to sequentially solve these following two linear systems. We firstly find the zk by solving that system, and then using zk, we actually can find ek. Why this transition is so important for us? Because these two matrices now, they share very important property. Particularly, they both so-called SDMM. So because some of you may be not familiar with the concept of SDDM, in the next slide I will present the basic definitions, the most important result for the SDDM matrices. So SDD matrix is the system of SDD system is a system of linear equations which has this form, m0x is equal to b, where m0 is SDD matrix, which means that it's symmetric matrix such that each diagonal entry of that matrix is greater or equal than the sum of absolute values of all non-diagonal elements in the row. The example of such matrix is, for example, the graph Laplacian. Now, what we can do, and our goal now is to find the approximate solution, epsilon approximate solution, where epsilon approximate implies that the m0 norm of the difference between the solution and the exact solution shouldn't be greater than epsilon multiplying the m0 norm of the exact solution. So this problem has been solved by Daniel Spielmann and Richard Penn, and in the solver they use the approximated inverse chain. Let me briefly mention how it's done. So in our method, we contribute to that literature by decentralizing their approach in order to make it applicable for our distributed fashion. So we start with the standard splitting of M0 matrix. We write M0 as the difference of D0 and A0, where D0 is the diagonal matrix that contains all the diagonal entries of matrix M0, and A0 is the matrix that contains all the non-diagonal one. And following the Spielmann and Penn approach, they noticed that the inverse of the difference D0 minus A0 is actually can be written in this way. And the crucial moment here is that this term here, it's also SDD matrix. Therefore, we can apply the same kind of decomposition for that matrix as well. As a result, and we do it recursively d times, where d is the length of the chain, and it characterized by size of order of log n. As a result, we construct the approximated inverse chain, the centralized one. And using that chain, we firstly find in a decentralized way the crude solution of the original system, where crude means that it's approximate up to some constant, not to any arbitrary constant, but up to some constant. And then in order to improve the quality of the solution, we use the decentralized version of the Richardson preconditioner scheme in order to make it epsilon close for any epsilon greater than 0. So, yes?
What is chain here?
Yeah, I will define on the next slide. So on the next slide, let me briefly describe. So I gave the sketch, and now let me briefly describe what do you mean under the approximated inverse chain. So as I said, repeating the same this decomposition for these matrices, we can construct the collection C of the following matrices: A0, D0, A1, D1, AD, DD, where each D K is equal to the D0 matrix, and each AK matrix is defined in this way. Notice that now we have the dependency to the 2 to the K power. So we proved that this collection of matrices satisfy the following properties. And we will refer this collection of matrices as an approximated inverse chain. Now, as we said, we decentralize Spielmann and Penn approach.
Rasul, you might want to explain this notation.
Okay. So the approximate here, approximate here. Can I use it?
Yeah, there was talk over there. On the wall?
Oh yeah, I see. So we say that two positive semi-definite matrices A, B related with that expression. It means that X transpose A x e to the minus epsilon. For any vector x. So basically, for small l, epsilon implies that they spectra are very close to each other. This is what we use when we define this. Okay. B0 is the demand vector. Remember that we start with M0x is equal to B0. That was our system of linear equations that we start.
So this is just a generic,
No.
strictly diagonally dominant.
Yeah. Right now I'm explaining
Right now he's talking about.
the solver part. Yeah. Then I will return to the problem description. So, as I said, we decentralize the Spielmann and Penn approach, and we start with the root approximation. And basically, the root approximation was given as in the following algorithm. So we basically sequentially construct the collection of B vectors. And then given that collection of B vectors, we started to construct the collection of X vectors. And the output vector, we prove that it's root. So it's approximate solution of that system up to some constant. Then in order to improve that, we use the decentralized version of the Richardson preconditioner scheme, which is nothing but the consecutive calls of the decentralized root solver. And the number of such calls is proportional to the log 1 over epsilon, where epsilon is the precision parameter that we want to achieve. So as a result, what we get the solver that can solve any SDDM system in a decentralized way with any arbitrary precision.
Sorry, maybe you should explain the Richardson scheme also a little bit more.
So in the Richardson scheme, in the Richardson scheme, we construct sequentially the set of vectors that is actually achieved by applying the root solver to the previous vector that we achieve. And we prove that if the root approximation satisfies some property, such that it's root, but it shouldn't be very, very bad. So we prove that the approximation value shouldn't be less than some constant alpha. Then we prove that given that we applying this scheme, we actually can get any arbitrary precision using these log 1 over epsilon calls. Yeah, for the like more detail, please. Yeah, I can actually give it on after the lecture. Okay. So, given that but now we want to understand how we can solve that system, how we can use our solver in order to find the Newton direction step. So, yeah, I think it's better. So, as we mentioned, in order to find the Newton direction step, we need to solve these two systems. On the first step, we solve that system. And because M is a block diagonal matrix, we can see that this system can be decomposed as a P systems, SDDM systems, where the matrix of the system is the Laplacian of the graph. And using our distributed solver, we can solve each of them, and we get these Z1 tilde k and ZP tilde k vectors, which are approximate solution. And then using that solution, our next goal is to target that system, the second system. And again, using the structure of the block diagonal matrix, we can decompose that as a collection of P SDDM system with the matrix, where the matrix of the system is the graph Laplacian. Yes?
So, with regards to the first step, so there the output is P solutions, approximate solutions Z?
Yes.
I'm a little bit
So-
confused with the indices.
So yeah, so K here actually is responsible for the iteration count that we consider. Okay, so we can actually right now disregard that. So assume that we're on some iteration. So assuming that we're on some iteration, solving that system is actually equivalent to solving P SDD systems that is distributed across the network. And what does it mean to solve it in a decentralized way? It means that each node I will eventually compute the ith component of each of these vectors, and will store the ith component of each of these vectors. Okay? So,
What is the number of the nodes?
I'm sorry?
P?
P is the dimensionality of the unknown parameter theta. The number of nodes is n. Okay. So the second step is to solve the second system, and in order to solve it, as I said, we can actually decompose it to the collection of P SDDM systems, where the matrix of the system is just a graph Laplacian. But here we must be very careful, because first of all, in order to solve it, we represent vector dk as a collection of these P n-dimensional vectors. And again, each node I must eventually compute the ith component of each of these vectors. And the crucial moment here is that these demand vectors B1, Bpk also must be distributed across the network. And actually, it's indeed the case, because we show that the rth component of each of these vectors can be found in this way. And notice that the only information now that node R need to compute that component, actually it's stored in that node, because the R component of vector ZL, it's inside of that node, and also the Hessian of the rth objective function, it's actually stored in that node. So as a result, what we got the epsilon approximate solution of the second systems, of the second collections of the systems. And now we want to ask a question, okay, so we use these two steps. In each step we find the approximate solution. But how these actual approximate solutions give us any arbitrary approximation to that original problem that we wanted to solve? And we actually proved that this is indeed the case. So if we introduce this notation, so Z1 tilde k, Zp tilde k is epsilon approximate solution of the second system. D1 hat k, dp hat k is the exact solution of this collection of systems. And D1 tilde k, dp tilde k is epsilon approximate solution to that collection of systems. So we actually proved that these two vectors are epsilon 1 and epsilon 2 approximations to the original system that defines the exact Newton direction step. And we proved that this epsilon 1 and epsilon 2, they can be made arbitrarily close to 0, as we want. So solving that systems, it leads to defining in the decentralized way the exact Newton direction, the approximation of the exact Newton direction with any arbitrary precision. And then we use that approximation in order to update our dual variable according to the Newton scheme. So that actually leads us to the distributed second order method, Newton method. And we recognize that this method has the following three convergence phases. So the first phase is called strict decrease phase, and it's characterized by this inequality here. It actually studies the difference between the difference in the value of the dual function in the two consecutive iterations. The right-hand side here, it's not either depends on the graph topology, which is encoded in these eigenvalues of the Laplacian, but also it depends on the small gamma and capital gamma. These are parameters that are lower and upper bound on the Hessian of the objective of the local objective that we assume are satisfied.
So you assume that the step size is 1 in all the iterations?
No. We assume that the step size is a constant, and in order to achieve that, we define the step size that actually leads to that.
Appear somewhere in the first phase, the strict decrease phase, we should have the effect of the step size somewhere.
It's already plugged in.
Yeah, it's already plugged in. We already simplified that. So we find already the expression for the lambda k, and we plug it in. But the thing is that this lambda k doesn't depend on k. It's just some constant that depends on these values, and that's why these values appeared here.
So you have a condition for the step size, right?
Yeah. So to get this theoretical guarantee, of course. So yeah, the second phase is a quadratic decrease phase that studies the change in the gradient of in the norm of the gradient of the dual function, and the last is the terminal phase, where the only guarantee that we can get is actually written here. So having introduced the theoretical part of the method, let me jump to the experiments and results. So we performed 3 sets of experiments. We made a linear regression problem, classification problem, and reinforcement learning problem. In the linear regression case, we consider both synthetic data that we made up, as well as the benchmark London School data set. In that data set, we have recordings of 30,000 students, where each recording is 27-dimensional vector. And the goal is to find the final scores on the test. On the classification side, the goal is we use the standard data set, the benchmark data set for the classification. It's called MNIST, and it's just a bunch of images of the handwritten letters, and we need to classify these letters. And for the reinforcement learning side, the problem is actually it's a control problem of where we try to control this system without knowing the model of that system. So we consider two cases, the simple math and double card poll in that case. We compare ourselves against the following 5 methods: distributed ADMM, proposed by Erwin Wei and Asuman Ozdagla; adaptation of ADD, where we just give another alternative way to compute the approximation of the Newton direction. This algorithm is actually based on the work of Mark Zagram. Newton network for Ian, distributed gradient by Nedici and Asuman Ozdaglar, and distributed averaging is the method that was proposed by Alex Olszewski. So in the next 2 slides, I will map briefly I will actually show the map between the regression formulation and the global consensus problem. So as we mentioned, the global consensus problem has the following form, and for the regression case, it can be written in this way, where each local function has the following form, and it can be simplified to the simple quadratic function by introducing these matrices pi, vector Ci, and scalar ui. And following our approach, introducing these unknown vectors y's, this actually can be written in a standard distributed GCP way. And the only thing that we should actually mention here is that in order to make the transition from the dual to the primal variables, that actually is required for our method. For this specific case, for the case of the quadratic function, this transition can be made using this closed form solution. And in general, it's not the case, and I will mention that for the classification regression experiments. And this is, on this slide, we actually show the results. So for the synthetic data set, we have 10 million data points, if each has 50-dimensional vector. And our performance is red, actually. So this is the comparison with the objective value. Yeah, because it's a log scale, they look like kind of like similar, the performance with, for example, ADMM. But if you look on the second picture shows the consensus error. So basically, this second picture shows how far these different thetas that we get for all these nodes from each other. Because our goal is to find the thetas that will be equal. So this deviation from each other, it should be as minimum as possible. So here we actually see that we significantly outperform all the existing methods. So we need basically just like 15 iterations to converge to the value with approximation 10 to the minus 14, where other methods require much more iterations to do it. So the same picture we observe for the real data set, for the London School data set. Now jumping to the distributed classification formulation, as I mentioned. So again, following the same procedure, we can rewrite that problem in the following way, where now notice that now for the objective function we have this logistic loss. And
maybe
also,
you should explain what this is so people know the formulation for the logistic. I haven't covered it in class. That's next week, so maybe say a few things.
Oh, okay. So for the logistic regression, so for the logistic regression, the goal is to find the parameter theta that will classify the bench of images correctly. So we have a training data set where we know the output, and we actually learn our parameter theta on this data set. And in order to find this parameter theta, the standard way is actually just this logistic function regression. So Yeah, and the objective, the regularizer here, it's actually, we consider both cases, L2 and L1 norm as a regularization. So for the, again, following the approach that we mentioned, we can distribute that in the following way, introducing these vectors. But now one thing I should mention, that now because this function now, it's not quadratic anymore. In order to make that transition from the primal to the dual, we don't have a closed form solution. And the way to handle that in this case is we apply just the standard Newton method inside of each node to that collection of the data that it has in order to get the primal value for the given dual variable. So, and this is the results on the classification. For the classification side, again, we outperform in here we actually more explicitly outperform both in the iteration count and for the precision is actually the same results. And
maybe you want to parse that picture a little bit more, say what because the colors are not clear from here.
Okay, so
tell us which one is which.
So we are red, so we reach this 10 to the minus 14 precision. Then the black one is distributed ADD Newton. Then the blue one is ADMM, distributed ADMM. And the green one is distributed averaging of Olszewski. We didn't put the Newton network because it was actually for this kind of dimension. We have like 256, so it's 16 on 16. So it's very highly dimensional space. And the Newton network was slower than this method. And actually, we didn't put the distributed gradient because also it was slow for these kind of dimensions. So,
what was the dimension? Tell us again.
So each image is 16 or 16 pixels. Each pixel is a feature, so it's like 256 for this case. Yes.
So there is a big, improvement, at least for the, let's say, the consensus error. Right? I mean, it's orders of magnitude.
Yes.
Can you, give some intuition about why this happens? Like, what's the mechanism?
Wait, so the intuition is that what's the fastest optimization method that we know to solve the minimization problems? It's a Newton method. Yeah. So what we basically achieve, we got the exact decentralized version of the Newton method. So that's why we actually can get these results, not just like so that's why the quality of each iteration of our approach, it allows us to improve the solutions in a very significant way. So the reason, the intuition behind that is just the quality of our approximation of the Newton direction is so good that it actually allows us to get this. Yes?
Yeah, sorry. How expensive is each one of your iterations compared
Yes.
to
Yeah, that's a very good question. I will refer that on the next slides, okay? Yeah, that's a very good question. Thank you. So and then finally for the reinforcement learning problem, let me briefly describe what the reinforcement learning problem is because, yeah, for some of you, you might not be familiar with that. So in the reinforcement learning, we have two entities. We have we have an agent and the environment. They interact with each other. So in the following way, the agent chooses some action, and the environment responds by giving some reward for the chosen action. So usually, traditionally, RL reinforcement learning problems are defined as a Markov decision process. They can be formalized by introducing these 5 components. So we have a state space X as a set of all possible states that agent can take. We have an action space. It's the set of all possible actions that the agent allowed to take. The transition probability is the probability distribution that defines the dynamic of the system. So basically, it defines what will be the next state given the current state and the chosen action. Then the reward function is just the reward that environment gives to the agent based on the choice of the action that it makes in the current state. And also it is a discount factor, which is just a scalar between 0 and 1. And the goal is to find the policy the optimal policy, which is nothing but the probability distribution of the all pairs of state action pairs, which means that for the given state, we want to basically find some optimal action that the agent should choose. There are different formulations for the reinforcement learning problem. The one that we will consider is called policy gradient. In that approach, we assume that state space and action space both are continuous. And the goal is to find the parameter theta. And we assume that this unknown policy, is parameterized by this parameter theta. And the goal is to find this parameter theta as a solution of this optimization problem. On the right-hand side here, actually is nothing but the total expected reward that the agent will get. So T here is the trajectory, which is nothing but the finite collection of state action pairs. And P theta of tau is the probability of the given trajectory, which is defined as in this way. And here we use the Markov property. And error tau is the reward that actually this agent gets choosing this specific trajectory. So typically, following the traditional approach for reinforcement learning, instead of finding the optimal of the objective function, which is defined here, to maximize the objective, we actually maximize the lower bound on the objective. And this lower bound can be achieved from the objective by just taking the logarithm and then applying the Jensen inequality to that. Doing that, we actually can get the lower bound in the form of the KL divergence of the two probability distributions. And then in order to optimize that, we find the gradient of that lower bound, and then we try to, and this gradient will be written in form of the expectation. It's actually stated here. And of course, because we don't know that expectation, this expectation towards to this unknown parameter theta, with respect to unknown parameter theta. Because we don't know it, what we do, we approximate that using that information, the training information that we have seen so far. So as a result, we can actually formulate the distributed version of the reinforcement learning problem in the following way. And again, for each local objective, what we'll get is actually the quadratic function, introducing again these matrices Fi, Gi, and Ui. And again, we solve it using our approach, following our approach, introducing these variables y1, yp, and the global consensus constraint. So this is the result for the reinforcement learning problem. So again, now we blue, and we actually observe the similar performance. Yeah, but we also add one. Yeah, we also add, actually it's the same amount of elements. So now let me answer on your question, which is a very good question. So yeah, you can ask, do we get all these improvements for the price of the communication overhead for the nodes of the graph? And the answer is no. And this is presented here on this slide. So here the y-axis is actually the accuracy parameter for the consensus error. So it's 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, minus 4, and so on. And the y-axis, it's the total number of local exchanges that the method should get in order that each method should get in order to achieve the corresponding precision. So as you can see, we read, and basically our performance is kind of like linear, where we proved that where on each iteration the total number of local exchanges that node should do is proportional to the condition number of the graph. Whereas for the others method, the total number of local exchanges that node should do is just a constant. But the place where we got the benefit is the total number of iterations. So just to simplify the explanation, assume we have two methods. The first method requires only one local exchange per iteration, but in order to converge to some solution, it requires 10 million iterations. Okay? The second method requires 1,000 local exchanges per iteration, but in order to converge to the solution of the same quality, it needs only 15 iterations. So now the question, which method is better in terms of communication complexity? Well, the second one, because the total number of communication that it needs is just 15,000, when the first one needs 1 million. So the this idea is just represented in that graph. So yes, you're right in the sense like the message complexity of each hour iteration is higher than the message complexity of each of these methods. But it's actually allowable for us because of the quality of our iteration that we get, and the quality is represented given this like very small number of iterations that we need to converge to the optimal. So as a conclusion, so what we get, we actually designed the first exact distributed Newton method to solve global consensus problem. We show that it can significantly outperform the ADMM approach, especially in the area of the precision of the solution. And we also show that it actually exhibits the superlinear convergence within the neighborhood of the optimal solution. So for the future work, we want to target the Hessian-free methods to scale up the problem. Also, we want to consider the stochastic setting to make it scalable even more. So we want to use the kind of like the technique that was proposed for the SQN method, stochastic quasi-Newton, or for the distributed BFGS that was proposed by Ariane as well. And finally, yeah, we want to try to test it for the lifelong machine learning problems. Okay, that's it. Thank you very much. Thank you very much for your attention. Now I'm ready to answer your questions.
Questions, comments?
I just have one comment. Like, I think it should be possible to eventually show that we converge to the exact solution, because your analysis shows that you get to a neighborhood of optimal solution, then you stop.
Yeah, we reach this terminal phase, and we just cannot give any guarantees for that.
If you run simulation, it should converge to the exact solution, because the point is dual function is strongly convex. No, it's not strongly convex, but it's strongly convex in the subspace that your gradients are. That's the trick that people use to prove linear convergence of dual ascent.
Say that again?
So, you know, dual ascent has a linear convergence, so you
Right.
converge to the optimal solution, right? So you have a superlinear first, then you stop, right? The point is the analysis of them comes from the fact that the dual function is not strongly convex, but it's strongly convex in the subspace that your gradient is, like same as the thing that we had in Mike's paper. But the point, I mean, also in that paper, like you should be able to prove exact convergence as well. Like if you try to,
Well, it depends on, because epsilon is not 0. Right?
No, it doesn't matter. Like even for gradient method.
Right.
As long as that's positive, then you should be able to prove convergence to the optimal solution. I think that the reason that you cannot get that is because of your using the line search, right?
Yes.
Yes.
So the thing is, if you use a constant step size, you can be able to.
But then with a constant step size, so okay, then you would get two different proofs.
Right.
If you use a constant step size or a decaying step size, you can prove exact convergence.
Yeah,
But then you could not, without playing with the step size, you can't get the quadratic phase.
Actually, that was something that we also observed in this for Newton. We had linear, superlinear, and then linear with constant step size. I mean.
No. I know that you observe it.
Yeah.
I don't think you can prove it.
Theoretically, there is a theorem saying that in an interval you have quadratic phase. But after, like, it's like the point, like, I can show you, like, you have a linear term, you have a quadratic term. When this quadratic term is dominant, you get quadratic convergence.
Yeah, when
the
eventually
the linear term will be dominant, and you get linear.
Yeah.
So
That's exactly, I mean,
Yeah,
that's
this is what we get.
what I'm saying is, if you use constant step size, you should have linear, superlinear, linear. But here, since you're using one, after some point, it's gonna stop, right? It's gonna stop at some point. You terminate, right? You have a terminate phase.
So the terminate, in sense, like it doesn't prove that it will stuck. It just so it.
Yeah, I mean, you cannot show.
No, what you're saying is you have to use, now you say, okay, I'm in some neighborhood, use some other analysis. Oh, but you're using step size 1.
No.
We use the not one. We use some constant step size, but not one. Yeah.
Oh, you don't use one?
No.
Even for the superlinear phase, you don't have the step
No,
size?
so to get these theoretical convergence phases, we actually give the closed form for the step size, for the constant step size. It's not one.
Even in the superlinear phase?
Yes.
Okay,
No, there is a subpart of the superlinear phase that step size would be 1, probably.
No.
The question is, if it's not 1, why do you use line search? You use line search to eventually set a step size equals to 1, right?
No. Why?
I mean, that's the whole goal. Like, you use a small step size to get into the neighborhood, and then you set it 1 to have the quadratic convergence, right?
Okay, so
I mean, I think it should be 1. I mean, maybe, because in even the ADD paper, like, you have line search, and then you eventually make it 1, and then you get that superlinear phase.
so
The quadratic phase.
in the proof that we use, we showed that the step size shouldn't be greater than some bound. Otherwise, we cannot get this quadratic phase.
That's for sure.
Yeah. So
It should be smaller than some.
if 1 will be like in that range, then yeah, we can actually use that. But in order to preserve that the quadratic phase convergence rate, the quadratic convergence rate, we this alpha k should be less than some bound, and we actually found this bound.
But we have to check to see if we can make it 1. And also, can we have an independent analysis that says,
About the
given
terminal
that
phase?
whatever matrix that this approximate Hessian that we always use is positive definite? I mean, at the worst case, we're doing some weighted gradient descent.
Yes.
Right?
Yes.
So therefore, we should be able to get exact convergence.
So okay, yeah, without actually coming to this terminal phase.
Maybe you need a different bound for this step size. I agree, but that's a parallel, analysis that you can have.
Yeah, but that's but not with this analysis. That's an additional thing.
Yeah. I know.
The problem is that analysis will not give you the quadratic phase.
I don't. I think you should be able to, because my point is you have this linear term, quadratic term, and then we can discuss that offline. But I guess I don't know. I'm not sure. But in network Newton we had that situation.
And you also prove that after the quadratic phase you get this linear. And
because worst case scenario you should be gradient descent, right?
yes, it's true.
No, but the issue is the step size.
No, okay. I'm saying like
If-
if the step size is smaller than 1, you should get linear. You should get exact number.
If your step size becomes small, then you should be able to prove exact
Yeah.
convergence.
Yeah, but it means that your step size should change with iterations.
No, you can get the you have some bounds, right? You take the minimum of all those bounds. If you satisfy that, you satisfy all the conditions, and you have all the things.
So find a uniform.
Okay, but are you sure that this uniform bound will not depend eventually on the iteration count k? It doesn't. Oh yeah, in this case.
But the performance seems to do really well experimentally on very large
Yeah.
things. So I think that's sort of the exciting part. And now we want to do this on the LHC data, right?
Yeah. So now we have 2 big data sets. One is from LHC, it's about the finding the boson Higgs data, and the
Higgs boson, not boson.
X, yeah, Higgs boson.
I think it's also interesting if you add because all the data sets that you are using are real data sets, right? But at the end of the day, it's good to have real data set, but it's good to have a synthetic data set that has bad condition number to show the advantage of this algorithm. Because I'm pretty sure you'll see even better performance for the case that the problem is ill conditioned. Just look at the quadratic problem and make the condition number very large. Then you will see more benefit for this.
Yeah, I mean, that's always a good trick.
Okay.
Because ADMM
If an ill-conditioned first-order methods do bad when the level sets of your Hessian are very skewed.
Yeah.
And Newton
Yeah.
corrects for that,
Yeah.
whereas first-order methods can't.
especially ADMM, I'm pretty sure ADMM.
Yeah,
So
that's
it's
true.
easy to make those fail.
Yeah, but
I thought that's sort of-
we didn't want to do it. Yeah, we wanted to compare it to
You have that to just justify the idea.
But it would be good also to try a bad mixing graph.
Okay, yeah.
So a
So
graph that has, it doesn't have to be very large,
yeah.
but
So
to look at
like
we
a
can construct
barbell
graphs
graph.
that are mixing of n cube time, right?
yeah, it's like a barbell graph. We have a click,
barbell,
and
yeah.
n
So
over
we do a
frame.
barbell graph with a
Yeah, for the barbell graph, a lot of algorithms will fail. But
No,
yeah,
that's the thing. We
Yeah,
want
yeah,
to
yeah.
say that when if
I
something
agree.
doesn't mix well, then all of these distributed algorithms will not.
yeah. For the GMLR paper, we're gonna try these different
Okay.
topologies.
Good.
Thank you.
Thank you.
Thank you.